Okay, and we're now recording. All right, so welcome back. Hope you have a good break. And we're heading into the home stretch, as it were. It's already April. And you should have gotten your exam score from me with the breakdown of points. That was a long time ago, I know, it seemed like. Right, so we only have chapter 4 and chapter 5 left. So we're over here, Monday the 5th. There's only about 7 weeks left. 1, 2, 3, 4, 5, 6, 7. So we have chapter 4 and a chapter 4 test and chapter 5 test and a final exam. Okay. Now, I am going to say something about exam 4. It might be a flexible day. For now, let's assume it's going to be Friday the 23rd, but I'm not sure I'll finish everything by that time, in which case I might push it back to the 30th. And we do have some extra days at the end. All right, so there's a chance I might push back the date of the exam 4. Plus, we lost a day. Not that I'm complaining, and I don't think you're complaining either. Thursday, the 22nd is a flex day. That's a CSM flex day. That means you don't have to go to any classes, but we teachers have to meet. Okay, so just keep in mind, I might, mind you, only a might. I'll let you know for sure, hopefully sometime around here if I see, oh, okay, we can keep the date, then I'll just keep it. For now, plan on keeping the date, but I'm just letting you know there's a possibility that I may not be able to finish everything on time, then I might push the exam back. We're not going to waste any days. If I finish this material, I'll just go ahead and start chapter 5 if necessary and keep going here. But I do have some buffer days at the end, just in case I fell behind. But so far, I've been able to sort of keep up the schedule. Okay, so that's what we have left. Okay, so we just got finished with chapter 3, our longest chapter. Right, so now we have chapter 4. There's a lot of graphing. Like the major topic of this section is graphing and some word problems. And then chapter 5, although for chapter 5, I'm including 4.9, just to let you know. Right, so this is our tentative schedule for now. So quiz Friday after that. And then not sure about the test day here. If we don't have a test, then I'll give you another quiz, obviously. Then the exam would be pushed back to here, but it won't change the schedule that much. So again, if I happen to finish chapter 4, let's say somewhere here or here, I'll just go ahead and start with 5.1 when it's not just going to waste time, so to speak. All right. Okay, so let's get started with 4.1. I snuck in very little of it before the break. That was like 10 days ago or whatever. Okay, so I'm going to run through that fairly rapidly, and then we'll get started with some of the homework problems from 4.1. Okay. All right, now, since I've already introduced the topic, I am going to go fairly fast on some of this stuff. Okay, page 276, maximum and minimum. Okay, so we've talked again about absolute maximum, absolute minimum. There's a very formal definition. You don't have to worry about it. Don't put it on your next cheat sheet. Okay, absolute maximum, absolutely the highest point of the graph. Absolute minimum, the absolute lowest point on the graph. They don't have to exist. Obviously, if I just draw a straight line like y equals x, there is no maximum, there is no minimum. Okay, and we have a local or relative maximum and minimum. Just within a small region, a small neighborhood, it's the largest or low or smallest points around. So local minimum. In that blue region, it's the smallest. Oh, there are other points on the graph that are lower, but locally, or relatively speaking, it's a minimum. Likewise, we can have a local maximum. Okay, so in this blue region, it's the highest point. Okay, there are other points elsewhere in the graph that are higher, but locally speaking, relatively speaking, it's a maximum. Okay, this looks like a local and an absolute minimum. And of course, we mentioned a long time ago, if you have an absolute minimum, you're automatically a local minimum. Likewise, if you're at a absolute maximum, then of course your local maximum also, but it doesn't work the other way around, right? You could be locally the highest, but not absolutely the highest, right? So again, the analogy in sports like the Olympics, if you're the fastest in the world, then you should be the fastest in your block, but not the other way around, right? You might be the fastest in your block, in your neighborhood, but that doesn't mean you're the fastest in the world, right? Okay, then we said local max, local min. It looks like there's a possibility where the derivative is 0, right? Maximum, minimum for this trig function. Okay, here y equals x squared. There's a minimum value of 0 at the origin. There's no maximum, of course, it goes all the way up and up and up. Okay. This is a closed interval, a function on a closed interval. The absolute maximum and minimum might be one of the endpoints, not because the derivative is 0, just because the graph starts or stops there. Okay, I mean, the way this graph is going, if you were to keep going, right, it looks like it would keep going up, 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 in which case this point would neither be a maximum nor a minimum. And same thing over here, right? So you might have a maximum minimum at the endpoints. So we have to consider that a little bit later. All right, so we have something called the extreme value theorem. I think it's worth putting that on your next cheat sheet. Okay, if f is continuous on a closed interval from a to b, then f attains an absolute max and absolute min. So a closed interval from a to b, continuous function, you have to have a maximum and a minimum. And we'll do some homework problems that involves that. Okay. In page 279, Fermat's theorem, if you have a maximum or minimum and a derivative exists, it's equal to 0. You can put it on your cheat sheet or not. I think once you get the hang of it, if you know what it's talking about, you know, it's quote unquote obvious, right? So if you look at a picture right here, right? Maximum, okay, derivative 0. Minimum, derivative is 0. If the derivative exists at all, it may not exist. Okay, so here's a minimum, but we know the derivative doesn't exist, right? It's a corner point. Y equals absolute value of x. Okay, and page 280, definition of a critical number. Critical number, it's in the domain. C is in the domain. The derivative is either 0 or does not exist. There aren't going to be that many problems where the derivative doesn't exist. Okay, quite often we'll set the derivative equal to 0. What's so good about having a critical number is it'll give you these possible maximum or minimum points. Not a guarantee, but you might have a maximum or a minimum. Okay. Closed interval method, we'll get to that in time, but I think we're ready to start some homework problems. All right, so page 283, we had 3 to 43 odd, 47 to 61 odd. Let me double check that that was correct. Because sometimes what I have in a book doesn't exactly match, but yeah. Okay. So it looks like we have a match there. All right, so 3. For each of the given numbers, A, B, C, D, R, and S, state whether you have an absolute max, local max, absolute, or local min, or neither. Okay, so A, B, C, D, R, and S. And in case you're wondering about the strange order, it actually kind of makes sense. They don't want to go A, B, C, D, E, because E is already used for something else, right? Base for natural logs, E to the X, and so on. And they don't want to say F, because F stands for function. They just go A, B, C, D, R, S. Okay, again, sorry, this is one of those where you have to just write it down. Again, if we were meeting face to face, I'd show this on the overhead and write on the board, but I can't do that now. So you have to write down all of this. Again, our abbreviation, absolute, just put ABS. Local, LOC, or I might say relative, REL. And maximum, just put max. Minimum, min. So let's use 3-letter abbreviations, okay? So how about absolute, ABS, local, LOC, relative, REL, maximum, max, and minimum, min. Okay, so tell me what all these points are. Okay, so again, sorry, I can't write it. You'll just have to write it for me. Okay, so A, that looks like a local max, right? So LOC, MAX. You can put relative also. I'll say relative because some books use that. So local max min, relative max min, same thing. Okay, how about B? Looks like a relative min or local min, right? C, local max. Okay, in a small region, in a neighborhood, it's the highest point around. Okay, D is nothing. It's neither a maximum nor a minimum, right? Because if you're standing at D, there's points that are higher. There's also points that are lower. So you can't say it's a maximum. You can't say it's a minimum. But if you're standing right here, right? Like you're hiking and you're right here. So yeah, it's a maximum. local maximum. Right? There might be other points that are higher, but locally it's the highest. Okay, so D is nothing. R, let's see, R is local and absolute minimum, right? So local min, absolute min. It's absolutely the lowest of the whole graph, and that automatically makes it relatively or local too. And S looks like absolute max and local max. Is that right? Okay, so that's pretty much it. That's the way it goes. All right, now 5. Use the graph to state the absolute and local max and min values of the function. Okay, so let's see, absolute and local max. Okay, so this is 0, 2. So again, you have to write this. So the point 0, to write it as an ordered pair, parentheses 0, 2, right, would be a what? Local minimum. This is actually something, even though it's discontinuous here. 1, 3, local minimum, right? Because if you go a little bit to the left, a little bit to the right, you only have points that are higher. So you can have a local maximum or minimum, even though it's not continuous. And about here, it's also a local minimum. So that's what? 2, 2, 1, 2, 1, 2, right? 2, 2, local min. And how about right here? That's what? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so 4, 5, absolute max, and then automatically makes it a relative max, right? And how about here? Looks like a relative min. So where's that? 1, 2, 3, 4, 5, 3. So 5, 3, put down 5, 3, relative min or local min. Does this point count as something, even though it's discontinuous? It's a local max, because if I go either to the left or to the right, you're only going down. Here it's way down. But I mean, imagine if you're hiking and you're standing right here on the cliff, it's a high point. Here you go a little bit lower, here you go much lower, but it's still a maximum, right? So relative max at what? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So 6, 4. And looks like there is no absolute minimum. When you have an open circle like that, okay, that means you're not including that point, which is what? 1, 2, 3, 4, 5, 6, 7, 1. It's not in a graph. There is no absolute minimum. Okay. There are points that are higher than 1, but you can't say 1.1 is a minimum. You can't say 1.01 is a minimum. You can't say 1.001 is a minimum. You can't say 1.0001 because you can always find something smaller. So there's no absolute minimum for this particular problem. Okay. All right, and let's see, 7 and 9. So I'll do 7. Sketch a graph that's continuous on bracket 1, 5, including 1 and 5, and has the given properties. Absolute max at 5, absolute minimum at 2. These are x coordinates. X coordinates. Local maximum at 3, local minima at 2 and 4. By the way, what's minima? It's the plural of minimum. 1 minimum, 2 minima. You're not supposed to say minimums. And likewise for maximum, the plural is maxima, M-A-X-I-M-A, 1 maximum, 2 maxima. I guess there's a car called a maxima, right? But here, when we say maxima, it's plural. 1 maximum, 2 maxima. You're not supposed to say maximums. And 1 minimum, 2 minima, not minimums. But anyway, okay. And oh yeah, let me give me the focus job again for those of you who don't have the book. Give you that and that. 13, let's see, I don't think we have any evens here, so I don't have to worry about evens. There's that, and that, and that. Okay, we have to go up to what, 61. Okay, so there's that. Some more there. Okay, so that should pretty much do it. Okay, 7. continuous on 1, 5. Absolute maximum at x equals 5. Okay, so I just have to make sure at x equals 5, I'm at the highest point. You see, what's the y coordinate? They don't tell us, so it can be anywhere. So notice I don't even mark the y coordinate. It's not important. It's just higher than anything else. Absolute min at x equals 2. So I just have to make sure that's lower than anything else. I decided to put it on the x-axis, but it doesn't have to be on the x-axis. Just lowest here. Then it says local maximum at x equals 3. So I have to make sure it curves down, but not higher than this, right? This is the absolute max. So I can't say bring it all the way up to here. So maybe just up to here. Local min at 2 and 4. But we already have the absolute min here. So if this is an absolute min, it's automatically local min. And a local minimum at 4. So I just have to make sure at 4, I go down and then up, just not any lower than the absolute minimum, right? Okay, so I'm restricted to not going below the absolute minimum, so down and up. So here's an example possible graph like this. Okay. All right, then 11. A, local max at 2, differentiable at 2. B, local max at 2, continuous but not differentiable at 2. All right, so we said from Fermat's theorem, 11a, if the function is differentiable, slope has to be 0. So what happens at B? Must be a corner point. So here's the example. Maximum of 2, differentiable means slope is 0, right? Think of the roller coaster going up and then down. So right at the very top, just for an instance, slope is 0. Okay, here, not differentiable, but continuous. So like so. Okay. All right, and so those of you that like roller coasters, and I heard they were starting to open up some amusement parks, weren't they? Pretty soon, but anyway, if you like roller coasters, if you're right at the top right here, slope is 0. Okay, I'll just go ahead and say they don't make roller coasters like this, right? It just doesn't look right. I'm not getting on that thing. It doesn't seem right, correct? So when you have a roller coaster ride, everywhere the graph is differentiable. It doesn't matter, if they go upside down and all over, it's smooth, continuous, and differentiable, right? This doesn't look right. I'm not getting on that ride. This is okay, right? All right, 13. Show you that one quickly. I'll just talk about A. Sketch the graph of a function on -1, 2 that has an absolute maximum, but no absolute minimum. Okay, so it must mean not continuous. Because if it is continuous, it has to attain absolute maximum and absolute minimum both. Okay, there's an absolute maximum, but no absolute minimum. So I made up a graph like this. Okay, here's an absolute maximum, goes down forever. It's defined everywhere between -1 and 2 inclusive. So here I just drew a straight line segment across. Okay, so it is defined everywhere from -1 to 2. There's an absolute maximum, but no absolute minimum. Okay, then part B, you have something much easier actually. Oops. 13b, discontinuous, but has an absolute max and absolute min. That should not be that hard to do. Okay. In fact, you can just start off with what they say, start off with a high point and a low point. Then the rest of the graph, just do anything as long as it's not connected, right? All right, so I'll let you figure the rest of that out in time. All right, so now moving on, 15 through 27-ish, sketch the graph and determine absolute and local max and min based on the intervals that they give you. Okay, so just getting you to have some practice on max and min, absolute max, absolute min, and so on. Then after that, critical numbers of a function. So critical number means derivative is 0 or undefined. Back here, critical number, page 280. Set the derivative equal to 0, or the derivative does not exist. Okay, since I already wrote it, I might as well get that out of the way. Number 29. Okay, I'll come back and do 15 and on, but simple example of finding a critical number. So take the derivative, set it equal to 0, and set it equal to undefined. Okay, so for like 29, we get that out of the way quickly. F of x equals 4 plus 1/3 x minus 1/2 x squared. Okay, so take the derivative. Remember how to take a derivative, right? It's been a long time since we did anything. So the derivative is nothing, 1/3 minus x, right? Set it equal to 0. So x is 1/3. So that's all. So this is called a critical number. That's all. And I'm also supposed to set this equal to be undefined. This is very well defined everywhere. Because when do I have to worry about undefined? Well, you know, taking the square root of a negative, denominator is 0, stuff like that. Okay, and yeah, I'm done with this paper, so let me do my focus job again. Okay. By the way, I heard from my superiors I might be getting a new document camera sometime. Might not be the rest of the semester, maybe next semester, but in the meantime, I got to keep doing what I'm doing here. Okay. All right, so that's it for that. All right, so now the 15 through 27, draw a quick sketch and talk about maximum and minimum values. Okay, so let me show you some of those. Okay, number 15, again, ignore any dates. F of x is 1/2 3x minus 1. X is less than or equal to 3. Okay. Now, I know this is linear. I could distribute it's mx plus b, right? I know the slope is what, 3/2 if I distribute. And it says x is less than or equal to 3. So what do I just plug in 3? If I plug in 3, I get 4, 3 comma 4. 3 times 3 is 9. 9 minus 1 is 8. Half of 8 is 4. I know it's increasing, moving left to right, because the slope is 3/2. So very crudely, here's the graph. All right, so what do I have? I have an absolute max at 3, 4, and a relative max at 3, 4. And it looks like there's no minimum. Okay, that's all. Okay, 21, f of x equals sine of x from negative pi/2 to pi/2 inclusive. And you might recall the sine of 0 is 0, goes through the origin. Sine of pi/2 is 1. Sine of negative pi/2, negative 90 degrees, is -1. So it looks like this. So it looks like maximum here, minimum here. So absolute max and relative max, pi/2 comma 1. Absolute min and local min, negative pi/2, -1. Okay. I'm going to use both relative and local just so you can get used to both. So REL stands for relative, LOC local. Okay. Some books use one or the other, so I want you to be comfortable with both relative maximum and local maximum or minimum. So you might see me switch it back and forth between the two. Okay, 25. F of x equals 1 minus radical x. All right, well, you can do some analysis on it. I think it's easier just to plug in stuff. You know you're not allowed to plug in negative numbers, right? I can plug in 0. What do you get when you plug in 0? 1. Plug in 1, 0. And if you plug in super big numbers, it just goes down like that, right? All right, so again, it looks like an absolute and relative maximum at 0, 1. And it looks like there's no minimum in this particular case. Right? Right, so that's basically how you do this kind of problem. So I showed you 3 of those of the type from 15 to 27. Okay, so I'll let you try some of the rest of those. Okay, now let me work on critical numbers. Okay, so that means take the derivative, set it equal to 0, and set it equal to undefined. And when we say undefined, it also has to be in the domain of the function. Okay, so I already did 29. Okay, and I'll show you some more. So how about I show you 33 from there. G of t is t to the 4th plus t cubed plus t squared plus 1. Okay, so take the derivative, g prime of t, 4t cubed plus 3t squared plus 2t, set it equal to 0. And yes, ordinarily I would say set it equal to undefined, but this thing is very well defined everywhere. Don't worry, I'll show you an example where it's not defined later. All right, set that equal to 0. Factor out the common factor of t. Then I have 4t squared plus 3t plus 2 equals 0. That means t is 0, or this thing is 0. Okay, now I can't factor it, so I use my quadratic formula, right? So t is negative b, negative 3 plus or minus the square root of b squared, 9, minus 4 times a times c, 4 times 4 times 2, divided by 2 times a. Okay, but notice this is going to be 9 minus what, 32? That's a negative quantity. We're only doing real math here, no imaginary, none of the square root of negatives, none of the I business. So that can't ever happen. So that means there's only one critical number, t equals 0 for this particular problem. Okay, all right, and 39 is actually a much harder problem. So let me start showing you 39. Capital F of x is x to the 4/5 times x minus 4 squared. Okay, not very nice. Okay, so it looks like a product rule. You guys remember the product rule? It's been a long time, right? Since before the break. So first function times the derivative of the second. Derivative of the second is 2 times x minus 4. Then by the chain rule times the derivative of the inside, which is 1. Plus second function, x minus 4 squared, times the derivative of the first. Derivative of x to the 4/5, 4/5 x to the negative 1/5. Okay. Quite a mess. Now, try to clean it up. I put the 2 in front, x to the 4/5 times x minus 4. All right, 4 is on top, x minus 4 squared is on top, 5 is on the bottom, x to the negative 1/5 on top means x to the positive 1/5 on the bottom. Okay, so everything in blue, ignore the red temporarily. 2x to the 4/5 parentheses x minus 4 plus 4 parentheses x minus 4 squared over 5x to the 1/5. That's my derivative. All right, so I can see automatically I have one critical number for the undefined part, x equals 0. Okay, x equals 0 is defined. I'm allowed to plug in 0 to the original function, but I'm not allowed to plug in 0 to the derivative. Okay, so because x equals 0 gives me an undefined derivative, that automatically makes it a critical number. Okay, so then getting back to the critical number thing, page 280. A critical number is in the domain of the function, and either derivative is 0 or does not exist. Again, I mentioned most of the time you don't have to worry about does not exist, right? I mean, the first a couple of problems we didn't involve it. Here's one example where you have to worry about the derivative not existing. All right. So again, x equals 0 is a critical number just because it makes the derivative undefined. All right. Now, set the original equal to 0. It looks pretty bad, okay, in red. To make it nicer, I multiply both sides by 5x to the 1/5. So that's what I'm trying to show you in red. Okay, to get a common denominator, multiply by 5x to the 1/5 on this side and this side. And of course, 0 times anything is 0, so that's still 0. But look at what happens over here. All right, if I take 5x to the 5th times this thing, the 5x to the 1/5 just cancels out. So I have 4 times x minus 4 squared, right? One more time. This expression, set it equal to 0 and undefined. I already know x equals 0 makes the expression undefined, but it is in the original domain. So that's automatically a critical number. Okay, clear the fraction, multiply by 5x to the 1/5. 0 times 5x to the 1/5, 0. 5x to the 1/5 times that will just be the numerator. Okay. Now look at what happens if I take 5x to the 1/5 times this. I have 5 times 2, which is 10. X to the 1/5 times x to the 4/5. What is x to the 1/5 times x to the 4/5? Add the exponents, x to the 5/5, which is 1. 10x, x minus 4. So this is not so bad after all. And 4 times x minus 4 squared. In fact, these two have a common factor of x minus 4, right? So factor out the x minus 4. This has a 10x. This still has a 4. All right, if I take out one of the x minus 4s, there's still another x minus 4, like that. Okay, so again, factor out an x minus 4. That's gone. I still have 10x. Take out one of the x minus 4s, I have 4 times x minus 4. Okay, multiply this out. I have 10x plus 4x, 14x minus 16 equals 0. Okay, so that does it. Okay, so now set that equal to 0 or set that equal to 0. Okay, so x equals 4. This one, you do a little bit of algebra, you get 16 over 14, which reduces to 8/7. All right, so the final answer is the critical numbers are 0, 4, and 8/7. Okay, so there was a lot to that one, obviously, as you can see there. All right, so that's that one. Let's see, what time is it? A little bit more. See if I have time to give you something to do in class. All right, so now for the remaining problems, find the absolute maximum and absolute minimum on a given interval. Notice they're all closed intervals, bracket, bracket, bracket 0, 5, bracket -2, 3, or whatever, right? So this is where we're using page 278, the extreme value theorem. If f is continuous on a closed interval from a to b, all the functions in this section are going to be continuous. F attains an absolute maximum and an absolute minimum somewhere in the interval. Okay. An example might be this picture. So the absolute maximum and minimum might be at a critical number, right? Slope is 0, slope is 0, slope is 0. But the maximum or minimum might be at an endpoint, as you can see from the picture. So that leads us to this stuff, closed interval method. Okay. Do you want to put this on your cheat sheet? I'll leave it to you. Maybe you want to hang off on it because look at how much writing there is. But if you understand the principle, if you know how to do the algorithm, you won't have to write it all down. Okay, but it's there, page 281. To find the absolute maximum and minimum values of a continuous function on a closed interval from a to b. In other words, this applies to 47 through 61. Okay, so 47 and 61, do this. Find the values of the function at the critical numbers. Okay. So the derivative equals 0. And find the values at the endpoints. You must look at the endpoints. And so you got a list. From that list, the largest y value will be the absolute maximum. Smallest y value, absolute minimum. Okay. So that's a lot to memorize, I suppose. And by the way, again, if we were meeting on campus face to face, I'd make you memorize this. So, I mean, you do have some advantages that we're doing this, all remotely. All right. So what is this all talking about? Okay. So all the functions they're going to give us from 47 to 61, they're continuous on closed intervals. Okay, so find absolute max and min. So let me see if I can set up one or maybe two. And if I have time, then give you something to do. 47. F of x equals 12 plus 4x minus x squared on a closed interval from 0 to 5. Okay. Do you recall what this looks like? Parabola, opening downward, right? Goes down. It's continuous. All right. Find the critical numbers. Set the derivative, right? So what's the derivative of this thing? Derivative of 12 is 0. Derivative of 4x is 4. Derivative of negative x squared is negative 2x. Set it equal to 0. You also have to say set it equal to undefined, but this is very well defined everywhere. All right, so x equals 2. Then I have to check the endpoint. So now I have 3 numbers to plug in. You always plug in the 2 endpoints, 0 and 5. And then you plug in critical numbers, like 2. Okay. Just tell you right away, like for 49, you automatically have to plug in negative 2 and 3. For 53, you automatically have to plug in 0.2 and 4. Okay, for 57, you automatically have to plug in 0 and pi over 2, right? For these kind of problems, you always have to plug in the 2 endpoints. They might be the maximum or minimum. Okay, and then what else? Any critical numbers. All right, so I plug in 0. 12 plus 0 minus 0, 12. 0 comma 12 is on the graph, right? So the only critical number was x equals 2. Okay, so I plug in 0. I plug in 2 critical numbers. Plug in 2. 12 plus 4 times 2 is 8. Minus 2 squared is 4. 12 plus 8 minus 4, 16. 2 comma 16. And then I plug in 5, the other endpoint. So I put 5 here, 5 here. 12 plus 4 times 5 is 20. Minus 5 squared is 25. That comes out to be 7. 5 comma 7. Okay. So one more time. Plug in the 2 endpoints automatically. Plug in any critical points. Now just look for the highest and the lowest y values. So the y values are 12, 16, and 7. So which is the highest? 16. Which is the lowest? 7. So absolute max, 216. Absolute min, 5.7. That's the way it works. Okay. And somehow this thing just stopped on me. So let me see why. Oh, I think I pulled the plug, literally. Okay, so let me see what I'm going to do here. Okay, you know what, folks? that would have been a good enough place to stop, and I would have given you something to do. I'm assuming you guys can still hear me. Can you all still hear me? Somebody, can you hear me okay? Or,
Yep.
yeah, okay. I can't get the camera working right now, so maybe it's better for me to just stop. And so I was going to give you something to do in class, but we can skip that and just end class here. So the last one I did was 47. So why don't we just stop there, and hopefully I can get this fixed by my next class or tomorrow. Okay, so let's just end class here. And yeah, anybody who joined late, please put it in the chat right now, so then I can get you for attendance. All right, so we'll just call it a day, folks. All right, thanks. See everybody next time. Okay, bye, everybody.